All right, class, we're going to finish up chapter 9 by talking about buffers. So hopefully you've gone through all the notes, and I just like to come in and clarify the more challenging topics per chapter. So as always, if there's more information or more clarification needed, please email your instructor or consult other YouTube videos or anything of that sort to help you understand this material well. So you should have gone through the pH scale, okay, to know that anything below 7 is considered an acid, anything above 7 is considered a base, and right at 7 is called neutral. Okay, so urine is acidic, human blood is slightly basic, so on and so forth. And of course, I told you that sodium hydroxide is a strong base, so it finds itself at 14 on the pH scale. Now we're going to talk about buffers. Buffers can be a little bit challenging, but we're going to get through this. So buffers are solutions that resist dramatic changes in pH. And so the idea is this, and I'm going to just try to explain this as best as I can. If you have something, and let's say it has a pH of 1, so it's pretty acidic, and here's pH 14, what happens is if you start dripping in some strong base to this, typically there is some sort of dramatic curve change, and it quickly goes to pH 14, or really basic. And so notice how quick that happens. I mean, you have that sliver of, I guess you can call that the amount of base dripped in before it completely changes. But how would you make it a little bit more stretched out to where you have a range? And that's where buffers come in. What they do is they help you stay in a tight range of pH. They resist dramatic changes in pH. And so if you had a buffer solution at pH 7.2 and it had limits to it like 7.2 to 7.8, it's going to take a lot of acid or base to really get it out of that range. So it kind of keeps you where you need to be without doing a dramatic change from 1 to 14 in the blink of an eye. So buffers are composed of a weak acid and the salt of its conjugate base. And what's not stated here is, or vice versa, okay? It can also be a weak base and conjugate acid. Now, the word conjugate might be a little bit confusing at this point. So let's say that you had a hypothetical HA, an acid, plus B minus going to A minus and HB. You would say HA going to A minus is a conjugate pair. And you would say B minus going to HB is a conjugate pair, in which this is your acid. And that would be called your conjugate base. That would be called your base. And this is your conjugate acid. Okay, and it can go either way. This is an acid on this side, and it has a base that corresponds to it on the other side. So that's what's meant by conjugate. Okay, so H3PO4 is a weak acid, and NaH2PO4 is its conjugate base. And so that would be an example of a buffer. And so you'd mix those two together. It would give you a certain pH, and you would likely stay within that pH until you overwhelm the buffer and you reach its capacity, okay? So the amount of strong acid or base in a buffer can counteract, okay? So that's the capacity. So there's a limit to how much a buffer can take before it does this and just completely goes off to the other side. So human blood actually contains a buffering system to minimize extreme changes in pH, which if our blood had extreme changes in pH, we wouldn't live. Okay, so it's the carbonate buffer system. That's why you exhale CO2. That's why whenever you exercise, you have the lactic acid. You can, and it increases the acidity of your blood if need be. And so you can look into that if you're curious. It's a very fascinating system, but we're not going to talk too much about it right now. And so here's a question. Do these make buffers? Nitric acid and NaNO3. Well, nitric acid, as seen on this list on the right-hand side, it's actually a strong acid. So no, that doesn't make a buffer because it's a weak acid and its conjugate base. Okay, well here is acetic acid. That is a weak acid. You don't find it on the list on the right-hand side. But mixed with lithium hydroxide. No. Lithium hydroxide not only is a strong base, but it's not the conjugate base to that one. The conjugate base to C2H3O2 would have been NaC2H3O2. the salt of its conjugate base, because the conjugate base would have been C2H3O2 minus, and then you would have just thrown an alkali metal on it, let's say Na plus, in order to make it a salt. And so no, 2 doesn't work out. H2SO3 it looks to me to be a weak acid because it's not on our list. And then LiHSO3. Okay, well that kind of looks like it could work. Okay, we have a weak acid, and then we have its conjugate base. Okay, weak acid, conjugate base. Because H2SO3, you subtract one of those protons to get HSO3 plus, and then you throw a counter ion. HSO3 minus, excuse me. Yeah, so that one would work. And what acid is needed to make a buffer with NaClO3? Sodium chlorate. So the acid needed would just be HClO3. Okay, HClO3. So remember, you need a weak acid and its corresponding conjugate base in salt form. Okay, so hopefully that clarified some difficult information for this chapter. And so here's some action of buffer demonstrated in this diagram, this scheme. And so you have the acid, you have the conjugate base. If you start adding more acid, what's going to happen is the base component of the solution starts accepting the H, thus keeping the pH about the same, and you can see that. Or if you were to add strong base to the solution, it's not going to just all of a sudden jump to pH 14, but rather it's going to steal the proton from the acid, as shown right here. And notice that now you have H2O, because whenever you add an H to that OH, you get H2O, and then you should have more AN minuses. Okay. Don't forget to check out this C.S. Lewis quote. It's very neat to see how a Christian scholar articulates so well what the Bible states and how reality is played out in the Christian worldview. So C.S. Lewis is one of a kind, one of the best there is in the last 100 years. So be sure to check out this quote. And I highly recommend also reading one of his most notable books called Mere Christianity, which is where this quote is taken from. Y'all have a great day.